I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
So welcome to episode number 53 of Physics Matter. So this monthly live colloquia series connects people worldwide to explore the popular science with a focus on capacity building in developing community and major research infrastructure like the Sesame Light Source in Jordan. So for more than 4 years now, so we have traveled virtually across the globe, like time, so which this month has been also traveling between continents. You see that, and you know that, time difference. So please, so in any case, you can visit our webpage and you can watch the numerous YouTube recording of those scientific exploration, so that are enabling global knowledge sharing. And today, so please participate live as well by raising your question after our esteemed guest presentation, which will last 40 minutes. So first, I would like to introduce the panelist, which is composed of Alan Hurd from Los Alamos, who has just been awarded APS Fellow. So that's what I wanted to mention as well. Bravo. And Johnny Mella for the ICTP, so in Trieste, and myself. So the three of us, I'm from the European Spallation Source in Sweden, but the three of us are former chair for the Forum of International Physics at the American Physical Society, which organization is supporting this series. So this week, so we have the honor to welcome for the second time Professor Malik Maaza, who was presenting last November nanoscience and nanotechnology towards sustainable development goal and the science with social impact. So in 2025, you know that we are the International Year of Quantum. So this is why live from South Africa today, so he will disentangle so the quantum trapping of cold neutron with picosecond precision. So Professor Malik Maaza, so he's the chair of the African UNESCO for the nanoscience and nanotechnologies. He's staff of the University of South Africa and through Heisenberg Lab and the National Research Foundation. So he's a fellow of various academies, so including the African Academy of Science, the European Academy of Art and Science, the New York Academy of Science, and the National Academy of Science in India, the Islamic Academy of Science, and the Royal Society of Chemistry in London. So in addition of this IUPAP, so the International Union of Pure Applied Physics, he has received so this Kenny Reed Award. So this is a medal that recompenses the outstanding contribution to the enhancement of physics in developing countries. So Professor Maaza has also received numerous awards. So for instance, also the Kame Kumar Award for the Excellence in Science and Technology, and also beyond all those awards, so the one connecting as well with the Presidential Makumba Order of the Republic of South Africa. So he has been the architect behind several continental and national ongoing platforms, so including the UNESCO and the UNISAT African NRF, so that is sharing, so for this nanoscience and technology. So the African Laser Center and the African Material Research Society. The African Light Source also, where he contributes, and recently as well, the African Center for Competency in in enhance nanoscience and nanotechnology for the sustainable development goal. So this is a lot to mention about his bio, but I think most important is that you raise the question as well to him at the end of this presentation. So you have a Q&A little box where you can prepare all the different questions, and we can give you as well the microphone to have you speaking and asking directly your question to Professor Maaza. So without further ado, so we have Professor Maaza now, so who will be presenting. Thank you.
Madam Program Director, dear esteemed colleagues, junior and senior colleagues present here, virtually or physically, allow me first to express my gratitude to the APS organizing committee here present and their team, wherever they are. And I wish also to express my gratitude to each and all of you for taking off your time and how can I say, attending this webinar. What I would like to do, colleagues, within the framework of this webinar, I would like just to share with you some of the findings that we were embarked in terms of fundamental science and at the interface of between different disciplines. Yes, indeed, you would see that it's nanosciences and nanotechnologies, but these nanomaterials or nanostructures do respond to fundamental sciences in relation to the standard model, to the cosmology, to the periodic table, as well as to the stability of nuclei. So this talk is given within the framework of the UNESCO, UNISA, Itamba Labs, NRF Africa Chair in Nanosciences and Nanotechnology, which is a trilateral partnership between the UNESCO Place Fontenoy in Paris, the University of South Africa, and Itamba Labs, which is a national facility of the National Research Foundation of South Africa. The NRF is the equivalent to the NSF, but with a certainly far below a smaller budget. Also, colleagues, this is, as it was mentioned by Madame Program Director, Professor Christine Darve, it is within the framework of the International Year of Quantum Science and Technology, for whom I wish really to commend Professor John Yemela and his team for their efforts in bringing quantum science to be celebrated within the UN and the international community as a whole. This talk, in effect, was a part of the International Year of Light, for which, again, Prof. John Yemela was one of the architects. The outline of my talk, if you allow me to do so, is first of all, I would embark in some neutron lifetime considerations, why the lifetime of a free neutron is important and why it's pivotal to cosmology, to the standard model somehow. Then I would share, if you allow me to do so, some basics of wave matter quantum neutron optics. Why neutrons, they do behave as a quanta, in what and why when they behave as a quanta, why they are very sensitive to gravitation, to electromagnetism, and the number of to the weak and the how can I say and strong forces. Then I will go after these two generalities and descriptions. I will share with you how we can trap cold neutrons in a nano structure of a Fabry-Perot resonator, and how we can trap him with the precision governed by the Heisenberg uncertainty, which means that you cannot have a better resolution, simply said. Then what we will do, I will share with you, if time allows, how we can modify that Fabry-Perot resonator by putting another layer whereby the neutron will tunnel through an extremely highly absorbing material. Normally, if you put a highly absorbing material, the neutron will not wave in, it will not go through. But quantum mechanics obliges, that is the beauty of quantum mechanics. In some conditions, the neutron behaves as if it's transparent and it goes through this highly absorbing material. And we will liaise all of these colleagues to the neutron lifetime and to the standard model. And we conclude by some conclusions and foresights, colleagues. Why the neutron lifetime is important? First of all, what we are dealing with is the free neutrons, not the neutrons which are bound in the nuclei. No, we are dealing about neutrons which are free, coming from a reactor or emitted by a nuclear, by a radioactive source. That neutron, when it's free, it has about 14 minutes and some seconds to live, and it will die. And the importance of this neutron lifetime is that it is at the early stage of the universe, which means at the Big Bang, initial, how can I say, it happened that the ratio between the neutron and the protons governs more or less the birth of the universe and the birth of hydrogen and helium, the light elements, colleagues. And in that regard, colleagues, physicists really have embarked extensively in it. Just to show just to quote some typical Nobel laureates who were more or less related to neutrons and directly is Ernest Rutherford from New Zealand, James Chadwick in the UK, Enrico Fermi, and Cliff Scholl. If I have just to mention these four ones only, directly, and Brookhouse in Canada, just to mention, colleagues, that a neutron has always been associated to a pure high fundamental forefront type science. But colleagues, recently the neutron has not stopped to interest the community, in particular free neutrons, the time life of a neutron, because it's related to the standard model, which, how can I say, of course, all of us, we are very well aware that Steven Weinberg, Abdus Salam, Sheldon Lee Glashow are related somehow to this, how can I say, the standard model, whereby the theory of unification. It happened that colleagues, I embarked to be interested by this, following the appreciation from the Abdus Salam ICTP, to whom I really, how can I say, I have no words to express my gratitude on behalf of myself, certainly, but on behalf of all the African community, each and all of them. I have had the chance to share the Nobel, to share the Abdus Salam spirit, the spirit of Abdus Salam with this highly, how can I say, commendable colleagues, Miss Concheta Mosca and Professor Adnan Shihabuddin. What is the relationship between the standard model and the neutron lifetime? A neutron consists of two down quarks and up one up quark. It decays after a free neutron after around 14 minutes and some seconds. It decays to give birth to a proton, an electron, and a neutrino via a bosonic relaxation. And as you can see, colleagues, this time, the lifetime of the neutron is around 14. I repeat myself, colleagues, to ensure that the message to take home, that what we are dealing with, it's not the cosmology, is not the standard model, whatever, is the 14 minutes end. So, colleagues, simply said that a neutron lifetime is extremely important to these equations. This a nice equation, you do understand it's a condensate in effect, but it is critical and pivotal to the existence of the Higgs boson and whatever related to how can I say, a gravitational component, space curvature, and so on. What I would like colleagues to point out is, please see these numbers here, 10 to minus 6 seconds and 10 to minus 32 seconds. This is the Planck constant time, more or less, and that is more or less the creation at the early stage of the universe, the creation of protons and the neutrons and so on. So, colleagues, the point that we are geared towards is to show that, in effect, when we try to trap cold neutrons in a Fabry-Perot resonator with an extremely high precision, and that the trapping precision is in the picosecond, 10 to minus 12. It is not 10 to minus 6, certainly, but it is not a second. It's not 0.2 second or 0.6 second, which is a limit of the current beam time and the bottle time. But just remember, colleagues, these numbers here, we are more or less dealing with a time in between here. The standard model, colleagues, is governed by a matrix, which is called the Cabibbo Kobayashi Maskawa matrix, which is the 3-3 matrix, colleagues. All the elements, all of them, except the M11, this one, all of them have been determined with a high precision possible and imaginary, except this first one. And this first one, colleagues, is the snag. This first one, the VUD, this one in particular, it depends on the neutron lifetime. And that is the snag, colleagues. This is the snag. We need to have high precision on n to have the high precision on the VUD, and therefore to the, how can I say, to the Kobayashi Cabibbo.
Ausstieg links. Richtung Oberhausen bitte in die Linie S3 umsteigen.
Sorry?
Sorry. Yeah. So please go on. I think there is a...
Yeah. So how can I say? The importance is to have high precision on this number, colleagues, here. And this one is the VUD, and this to have a high precision on this term here, we need to have to measure with a high precision to n, the neutron lifetime, as you can see. Unfortunately, colleagues, since Norman Ramsey has embarked in, how can I say, in the investigation of the neutron properties, it's a dipole, it's a, how can I say, there are two major techniques that is called the average beam method and the average bottle method. Since the 80s, colleagues, as you can see, these techniques were indeed measuring the neutron lifetime, but with the, how can I say, the bar error on these values are very high. Within the time, this precision was coming more and more precise, but, colleagues, as you can see, both for the average beam method as well as the bottle method, this bar error was diminishing. But colleagues, as you can see, the two techniques are giving average times which are different by 10 seconds. And this in within the years, colleagues. And these 10 seconds here is of a concern. We need to have, in the standard model, what is the value that we have to take? Is it this average one or this one? So up to now, the two communities are not yet, they are talking to each other, but there is no, for the moment, there is no clear decision about the neutron lifetime. So the idea, colleagues, is to find out a potential other approach, because with the beam approach, the precision is plus minus 2 seconds. With the bottle method, it's plus minus 0.6 seconds. Of course, both of them, how can I say, it's a smaller, but still 0.6 seconds, colleagues. Recently, there was an experiment indeed by, how can I say, quite a broad team in the US, where indeed they have measured also the neutron lifetime with a better precision, but the bar error is also high. It's not in the picoseconds, but maybe, I do not remember, colleagues, what was the recent results. Maybe some colleagues here could correct me that Nonetheless, colleagues, it is necessary to reduce or to enhance the precision on the time life of the neutron lifetime. We need to find out another approach, and it is in this regard, colleagues, that we propose that we should go using cold neutrons or ultra cold neutrons, the most ultra cold possible. Why? Because in this configuration of ultra cold neutrons, it is the wave aspect, the wave packet aspect, which takes place from the corpuscular one. And in that regard, colleagues, how can I say, why it is extremely important also, it's not only the standard model, because all the elements of the Mendeleev table so far are governed by the beta decay of the neutrons. As you can see, here is the chart, the perspective, the chart perspective giving a birth of the different elements and isotopes, whatever, but certainly the most stable fellow elements. As you can see, it's dominated by the blue and the orange, and these are the beta decay. Plus or minus the beta decay, it's the neutron lifetime related. So, colleagues, you do understand from nuclear science point of view, it is critical. One, from the Mendeleev table, colleagues, it is extremely important that you would understand, colleagues, that the early stage, it was hydrogen and helium, but it was the neutron acting like a glue in the nuclei, which was really pivotal to form all the other elements. Therefore, I must say, I can state, according to my knowledge so far, that the death of a neutron gave birth to the periodic table. Colleagues, still in the Mendeleev table, still we are producing other elements which are a short lifetime, certainly, okay, but it is still the neutron, the bombardment with the neutrons, that allow us to have a non-stable element, but nonetheless they are heavy. So the neutron plays a role still in enriching the Mendeleev table, as here, for example, by Oganessian from the Joint Institute of Nuclear Research in Dubna in Russia. Colleagues, the results that I would share with you, in effect, they are summarized in a paper here, which was published last year, early, I think. It was in Journal of Neutron Research. But these results, in effect, colleagues, it was not a once-off. No, it was a part of a long marathon, which has started in 1987, when I was a student at Commissariat l'Énergie Atomique, interacting with colleagues from the NIST, from Oak Ridge National Laboratory, from Lansky, and Grenoble, ELL, and other sources. As you can see, we have played extensively with the neutrons, both by using deviating them, polarizing them, splitting them, and observing tunneling phenomena, as well as the Zeeman, and using them, preparing the supermirrors, monochromators, and so on and so on. So, colleagues, the neutrons that we are dealing with are cold neutrons. These cold neutrons, their energy is less than 0.025 electron volts. These are the ones that we are speaking about. And their energy makes them in a way that their wave packet aspect or their wave behavior is observed at room temperature. And we are not dealing with the thermal, epithermal, cadmium, what. No, cold neutrons. And in that regard, colleagues, it's the wave nature which takes over, and therefore purely quantum mechanic driven phenomena. And colleagues, simply said, a free neutron or a neutron propagating in a medium with a potential VR is described by the Schrödinger equation, as you can see here, colleagues, where the potential is given by the Fermi potential, as you are aware. And if you play on the equation here, you will get the Helmholtz equation, and this medium depending wave vector divided by the wave vector in medium, it will give you the refractive index, and therefore, colleagues, with the Helmholtz equation and the refractive index, that means, how can I say, colleagues, that means, sorry, a neutron, a cold neutron will not see singular scattering points, but rather a continuum, and this continuum medium has an average refractive index given by this simple formula, and this simple formula, colleagues, sorry, this simple formula is equivalent to the X-rays, 1 minus delta. Delta is of the order 10 to minus 6. The same thing here, colleagues, is 1 minus delta, and this delta is of the order of 10 to minus 6, except that in the neutrons, you are dealing with the nucleus, and therefore with the nuclear scattering length amplitude of the nuclei, and while with the X-rays, you are dealing with the, how can I say, the Z number, of course. If the refractive and the total reflection, colleagues, which was observed by Enrico Fermi and Marshall in Illinois at the Argonne National Laboratory, is the equivalent. It's the equivalent to the total reflection in fiber optics. You remember, colleagues, when we send a beam on at the interface between a high index and low index, the beam under certain conditions, it will be totally reflected. That's exactly the same thing with the neutrons, except that with the neutrons, colleagues, this angle here is extremely small. It's less than a degree, and therefore you need to have a highly collimated beam. If so, you will be indeed finding materials which would totally reflect the neutron beam. It can be totally reflected like this, like in a fiber optic, and so on and so on. So this total reflection was the first manifestation of the quantum behavior of cold neutrons as observed by Marshall and Enrico Fermi in Argonne National Lab. This total reflection is of an interest quite extensively for extending the nuclear reactor by creating what we call neutron guides, which are the equivalent of a fiber optic, moving cold neutrons from the cold source in the reactor towards the hole here, and building additional spectrometers far from the reactor, therefore with the low background, but also with neutrons with the large wavelengths, and these large wavelengths can be used for a polymer, for condensed matter in general, and soft matter, polymers, solids, magnetism, name it. It is not our focus today here. What we are focusing in is the optical properties or the wave behavior of cold neutrons in line with the quantum mechanic principles. And once the total reflection was observed with the cold neutrons by Enrico Fermi and Marshall, the neutrons were polarized by Arsène Gukasov. Then Meyer Leibniz has showed that we can have an interference with a neutron beam in 1962. 1 year before I was coming to this word, and Drabkin also has validated magnetic polarization, and so on and so on. The top of the range is that when Helmut Rauch, one of the students of Schrödinger, Erwin Schrödinger, has demonstrated with his colleagues from the US, Colella and so on, in Missouri, have demonstrated that we can have a neutron interferometry. That is interferometry with the precision of a wavelength of around, how can I say, 0.1 angstroms. And it happened that the colleagues, the results that I will be showing you, the idea was not mine. It was Helmut Rauch who gave me this problem, but I was not aware what he was looking for. And he was an old style boss, and well, the student has to do what the boss has said. Anyway, it's 20 years after that I understood what I was looking for. Anyway, colleagues, the point is that nearly all the optical phenomena were observed with the neutrons according to quantum mechanics. In this case, colleagues, what we will do is the following. We will take a nano-scaled Fabry-Perot resonator. A Fabry-Perot resonator, colleagues, consists of two mirrors, highly reflecting mirrors, separated by transparent medium. That is the Fabry-Perot standard one, except in our case, we are taking a thin film here. The mirror here is a nickel. The transparent material is titanium or vanadium. Nickel has a high nuclear scattering length amplitude, so it will reflect back the neutrons, in particular called neutrons, while elements like titanium, vanadium, and so on, they have a negative nuclear scattering amplitude. Therefore, they behave as they are transparent to neutrons. So in optics, if we send, or according to quantum mechanics, if we send a neutron beam, this neutron beam will be totally reflected. And can I say, specific conditions here, as we said, we put ourselves as we are reproducing the experiments of Enrico Fermi and Marshall and Zinn. We send a neutron beam here, colleagues. We send a neutron beam. I am really lost with my an arrow. It's okay. We send the neutron beam, colleagues. Normally is totally reflected, but colleagues, it happened that in some conditions, this neutron beam, this neutron wave packet coming on the first reflector will tunnel, because we have a quantum well, colleagues. We have a quantum well, and quantum mechanics tells me if the potential, the thicknesses, and so on are chosen in a way that the resonance condition is filled. So therefore, this wave packet here, it will not be totally reflected, but it will tunnel. And if it will tunnel here, because the thicknesses here and the properties of this first reflector are the same one as the second one. Therefore, the neutron wave packet which has tunneled, it will tunnel a second time, because it's a symmetric quantum well. And therefore, we will have tunneling. Therefore, if we put a detector here, what is not reflected will be observed in the transmitted beam detector. That's exactly what we are looking for, colleagues. And in our case, that's exactly what we are looking for. And therefore, colleagues, this is the curve that we obtain when we send a cold neutron on our Fabry-Perot nano-resonator, consisting of a highly reflecting material, nickel a mirror, and the second nickel mirror, but separated by transparent material, that is vanadium or titanium. What we see, colleagues, when we attack under total reflection, normally all the beam has to be totally reflected, as per Fermi and Marshall and Zinn. No, colleagues, when we take this configuration, what we observe that in some conditions the beam there are dips in the reflectivity profile, and these dips do correspond to a beam here detected by in the transmitted beam, and that's exactly what we have, colleagues. Here is the total reflection, the reflected beam versus the wavelength here, because we are using a white beam, a polychromatic beam, not a monochromatic one. And colleagues, what happened is that in the total reflection plateau, which starts here, we see clearly that there are dips. Normally, according to the total reflection, we wouldn't have full of pink points, all of them here in this plateau. But unfortunately, which is not the case, indeed, we have some which are there is one reflectivity equal to 1, but there are dips here. And these dips do correspond to peaks observed in the transmitted beam. This is the reflected beam, and this is black is the transmitted beam. You would see that all the dips related to observed in the total reflection plateau, they correspond to a beam detected by the transmitted beam. And as you can see, colleagues, they do correspond to that. This, what does it mean, colleagues? That means that this, how can I say, there was a partial total reflection, and those who were not reflected, they have been tunneled, and the tunnel the second time and were observed by the detector, colleagues. You would understand, colleagues, that here, first of all, what we can deduce, this is quantum mechanics at its most beautiful behavior. If, how can I say, if quantum mechanics was a person, that person will be magnificent forever. Colleagues, here, what does it mean? Here we see a total reflection behavior and the transmission. What does it mean? That means the Broglie relationship, that according to quantum mechanics, our neutrons, they do not behave like particles, but as a wave packet. One. Second, we observe the total reflection. That means we are reproducing something equivalent to Enrico Fermi, Zinn, and Marshall. Three, we observe that there is a tunneling, and if it is tunneling, that means that what is observed here, in particular the width at half maximum, will be governed by the Heisenberg uncertainty and nothing else. Voila. And in that regard, colleagues, how does a neutron wave packet behave? Well, the unique way to image that we are allowed ourselves to give is to say, oh, some, how can I say, these peaks here, the dips in the total reflection are related to somehow wave packet which have tunneled. Some of them, they will be with the tunnel straightforward and come tunnel a second time straightforward. Others will be reflected twice and third time, and the third time, second time, boom, they will tunnel, and so on and so on. That means these dips here, they do correspond to different resonances and to different wave packet tunneling within the Fabry-Perot resonator. And the longest one who would be trapped are the ones who would, how can I say, who will spend quite a long time in the Fabry-Perot resonator. And that is that the time spent by the wave packet trapped in the resonator is given by the Heisenberg uncertainty. And if we do our calculations, colleagues, this is what we find. We find that the trapping time with the large, how can I say, it's in the picosecond regime, colleagues, as you can see, at the large wavelengths here, they can be trapped for a longer time, and you know, but the trapping line time, colleagues, the precision is in a picosecond, 10 to minus 12. It is not plus minus 2 seconds. It is not plus minus 0.6 seconds. It's 10 to minus 12 seconds. Now, colleagues, how can we go further? Well, you would see, colleagues, you will plot the time life of trapping versus the, versus the wavelength. You would see, colleagues, that the larger the variation is quadratic. That means if we want to trap for a longer period neutron, we need to have an ultra cold source, very intense one. That is why ESS, the European Spallation Source, and advanced sources have to come in, colleagues, because the variation here of the trapping is quadratic to the wavelength. As I mentioned, colleagues, that is why we needed to have on the sample itself around 10 to 18 flux, 10 to 18 neutron per centimeter cube on the sample itself. And therefore, it's not possible to do it with the normal ones. Here, it's just a validation of a trapping. It is not as advanced if we want to trap as long as possible and to measure this trapping, it is we need to have an intense sources. Now, colleagues, better than that, what would happen if we couple these resonators? What if we couple these resonators like this? Can we, how can I say, if the wave packet resonates through the first resonator, it must resonate. That is quantum mechanic. It's symmetry. How can I say? It's symmetric. But colleagues, what we will do here, we will do something better. Above the previous one, for trapping in one resonator, a single one, we took a highly reflecting material, nickel, and the transparent material, titanium or vanadium, and so on. But when we couple, colleagues, the behavior of a neutron is extraordinary, and that can be only understood by quantum mechanics, not classically, is that we will, instead to take a highly reflecting material, we take an extremely highly absorbing material. But if we take a highly absorbing material, colleagues, you would say, no way the neutron wave packet will be absorbed. It can't be. No, c'est faux. C'est pas vrai. Because this quantum mechanics, when we couple the resonators and when we choose the thicknesses of the highly absorbing material and the transparent material in a correct way, that some phenomena, quantum mechanic behavior comes out, and it just cannot be explained classically. And colleagues, one of the highly absorbing material is boron. A natural boron has around, and the most highly absorbing is boron 10. And in the natural boron, colleagues, around 20% of boron is boron 10. So therefore, there is the probability of this neutron, classically speaking, is zero. But quantum mechanics, it is not. Specifically, colleagues, when we take, how can I say, I don't want to explain why we are taking the boron and so on. What is sure, colleagues, if you take a how can I say, coupled resonators, you are obliged to consider what we call Zeldovich-Vinogradov configuration. And the Zeldovich-Vinogradov configuration was used extensively in X-rays, in particular using this machine that is used for sub-nano lithography, for example. Why? Because if you want to see an extraordinary quantum mechanic phenomena in these coupled resonators, the thickness, colleagues, must be controlled at a ±1 angstrom. What does it mean, colleagues? Is ±1 atom size of an atom. You do clearly see, colleagues, it is extremely challenging, and I was really extremely lucky to be surrounded by beautiful minds, extraordinary men and women who allowed me to reach this. So, colleagues, generally speaking, if you take Schönborn or if you take any neutron optics in any neutron research center, we use multi-layered systems like this. And this multi-layered system like this, they consist of highly reflecting, highly transparent material, and so on and so on. When you do that, colleagues, when you send a neutron beam, the neutron beam initially, it will be partially reflected and partially transmitted. At each interface, colleagues, like in optics, it will be, how can I say, it will be partially reflected and partially transmitted and so on. These partial reflection at different interfaces, they will give you what we call Bragg diffraction. Okay, it's a peak that you would see clearly in the reflected beam. Now comes this peak here. This first partial beam reflected at the interface between the air and the multi-layered system, or the artificial crystal, if you wish, and the interference between this beam here and this beam coming from the substrate will interfere, and they will give you what we call Kiesig fringes, because they are related to Kiesig resonance conditions. Now, colleagues, in our case, we how can I say, in the classical case, colleagues, in any neutron optic or how can I say, they use this configuration where the thicknesses of the reflecting material and the transparent one are nearly equal because the refractive is close to 1. But colleagues, so when you take a highly absorbing material, transparent material, which means when you couple our resonators, instead to take a nickel vanadium or nickel titanium, you will take a boron carbide and the titanium as a transparent boron carbide and so on. If you remember, colleagues, we said that if the neutron wave packet sent here at a certain certain angle, though it will be partially transmitted, reflected, and partially transmitted. You would understand, colleagues, classically speaking, you would say, no, it will be absorbed, and it will never reach the substrate. No, c'est pas vrai. It's not right. It's wrong because the quantum mechanic, when you take what we call Zeldovich-Vinogradov configuration, then, colleagues, their behavior, how can I say, the wave packet behaves differently in a way that inside, colleagues, in the side resonator here, the neutron wave packet will, can I say, will behave in a way that the maximum interference is in the middle, while the minimum of interference will correspond to the absorbing material. If there is a minimum of interference in the absorbing material, which means the absorbing material has, or the probability to be absorbed is nearly 0. And indeed, colleagues, when you do the probability of psi star calculation, you will find out its maximum in the middle, which means in the transparent medium, and the probability to find the neutron wave packet inside the absorbing material, it is nearly 0. And therefore, colleagues, what does it mean? That means I will be able to observe Kiesig fringes, because this wave packet and the one which came at the bottom, from the bottom, I will observe it. And I will say that the ones that will be partially reflected at each end, each interface, here, they will give me a Bragg peak. Is that possible? Well, colleagues, at least we said that quantum mechanics tells us, if I prepare my sample in a way, I have these conditions here, what I will have, how can I say, this wave packet transmitted, tunneling through the first resonator. There is no reason for which it will not tunnel through the second resonator, and so on, until it will reach the substrate, it will be reflected, and so on, which means my wave packet is likely to be go down and come from the bottom of the substrate and come out and interfere, and to give me the Kiesig fringes as well as the Bragg peaks. Well, as St. Thomas, we believe what we see. What we see, colleagues, is the following. Here we see a Bragg peak, colleagues, which means there was reflections at different interfaces here. That's what it gives me, the Bragg peak. But better than that, colleagues, it gives me Kiesig fringes. If I zoom here is, colleagues, the Kiesig fringes, and that means that the neutron wave packet went down. This one has interfered with this one to give me these Kiesig fringes, and as you can see, the contrast is not perfect, but it's good, colleagues. What does it mean? That means this wave packet came out from the bottom, which means that this one, it has traversed, went, tunneled many times, as much as the number of resonators, and came out to give me this. So, colleagues, here, first of all, what we can conclude is, once again, the neutron wave packet behaved, the neutron behaved as a wave packet and not as a corpuscular component governed by the Broglie relationship. 1. 2. So the neutron wave packet behaved as it is observing, it is tunneling. Therefore, Heisenberg uncertainty is involved. 3, colleagues, the different resonances are within the coupled resonator. That means it tells me that, who tells us, sorry, that we are in a structure of the, how can I say, the strict configuration of the Zeldovich-Vinogradov, and that is such, all this behavior are purely quantum mechanic driven and not classical one. And colleagues, you would understand that these Kiesig fringes, they are equivalent to the X-rays, and it's again a confirmation that neutrons wave packet, they do behave as an electromagnetic wave polarized in a state. And here, colleagues, it's beautifully, these are the Kiesig fringes. Of course, it was done on not on the Léon Brillouin laboratory neutron reactor. It was not very intense, it's not around 10 to 14 neutrons flux. But imagine if we can do this with cold neutron, ultra cold neutrons, that will really take the neutron physics at a really high level. But colleagues, allow me, please, I beg your pardon, to allow me to share with you this. Remember, colleagues, the thicknesses that we have used of the boron carbide, it was around 2 nanometers. 2 nanometers and 120, two, I don't want to say something wrong, colleagues. Yes, it's 2 nanometers, colleagues. 2 nanometers. And the other one is 120, a transparent one. But you do understand, colleagues, that 2 nanometers, you may say that it's thin. No, remember, colleagues, we are attacking, if the real thickness of the boron, the absorbing material, is 2 nanometers, the beam is tackling or impinging the absorbing materials at an angle of around 1 degree. Therefore, in effect, the neutron beam path is not 2 nanometers, but it's 2 nanometers divided by 10 to minus 2, and that is 200 nanometers. Colleagues, you would appreciate that a neutron with a specific cross-section goes through a hugely, significantly, highly elevated absorbing material, traversing nearly 200 nanometers. It should be absorbed, but it is not the case, colleagues, because quantum behavior and propagation of the neutron beams. Again, colleagues, what was shown are preliminary results in relation to the precision that can be achieved in the picosecond regime within this way, relatively to the beam and the method, as well as to the bottle method. And it is expected that hopefully new generation ultra cold sources would allow to trap for a longer time and have a higher, better precision, or maybe to couple the beam method with the tunneling, the Fabry-Perot resonator, or the bottle, putting it in the walls of the bottle beam, the bottle itself, trapping configuration to put inside the colleagues a Fabry-Perot resonator. And knowing also, colleagues, when we use the boron carbide here, the boron, if the neutron is absorbed within the boron carbide, you may say it might be, yes, it will emit a gamma and an alpha. So we can identify easily the neutrons which have traversed or went through the Fabry-Perot resonator and the absorbing material specifically, and those who have been propagating within the resonator, because if they are absorbed by the boron here, they will definitely emit a very intense gamma ray, as well as a helium, how can I say, a helium. So therefore, alpha particle. And therefore, colleagues, it is possible to identify if the neutron is absorbed by the absorbing materials or not, because we can put some proton from alpha detectors and gamma detectors surrounding the Fabry-Perot resonator, or the coupled ones. And by that, colleagues, I think what is sure is that the cold neutron source at ESS in Lund is really promising to reach an extremely high flux. If it is the case, this kind of physics will bring us more or less to another forefront of neutron physics. That's one. But colleagues, above the fundamental aspect of the neutron lifetime, you may have noticed that in effect what we are working on is that we are bringing the sciences at the interface and dialogue, interacting in the terms involving a dialogue between different disciplines. That is material science, that is condensed matter, that is neutron physics, that is quantum mechanics, and so on and so on, and the cosmology and the deep nuclear sciences, that is the quark type sciences. And by that, colleagues, I thank you. I wish just to finish by this quote of late Madiba: "It always seems impossible until it's done." And this work was done involving quite a number of African colleagues, but quite a number of colleagues from the North, showing the importance and the critical role of a North-South and South-South cooperation. And I wish to express my gratitude to the APS and all the organizing team members here, and each and all of you for taking off your precious time and attending this seminar. Thank you. To you, Program Director.
Thank you very much for this very nice, comprehensible, so with a good neutron background, indeed a bit more technical than typically, but I think it's perfect for our scientists. So we hear that there are already a few questions, and I kind of saw also for the case of DSS how indeed it could be very useful. So we'll start the question maybe with Alan, and then I will go on the question and answer box. So please, Bill.
Yes, perhaps Maaza would turn on his camera. That's your choice. Your choice.
Sorry. No, I do apologize. I just want to put in some broadband. Sorry.
You know, I very much enjoyed the description of the discrepancy between beam methods and bottle methods, showing the disagreement of about 10 seconds in the neutron lifetime. I believe I captured that correctly. That reminds me of the crisis in cosmology, you know, regarding the Hubble constant and the disagreement between different methods. And the reason that is so famous is just simply that I think maybe various cosmologists invented that term, and it brought things to the attention of the public. But it's a very fundamental disagreement in Hubble constants, and a very fundamental disagreement that really underpins the periodic table for neutron methods. So or neutron lifetime. I just wondered if there is any interest in the scientific popular literature about this issue.
I must admit, Alan, there is definitely an interest, and in effect, the community who is involved in this type of studies, they do not publicize much. They do not bring it to the public. They are only, you go, they are more or less, it's like a marathon to who will be publishing in Science and Nature, say I am the first. And we neglect bringing this outstanding know-how, fundamental basics to the community. I think the colleagues are not doing enough, and it deserves it.
Very much so.
Thank you. And concerning the cosmology, that I must admit, Leonard Susskind at least is extremely prominent when it comes to this, because he's bringing these problems of cosmology and other related matters to the public in a very simplistic language. I think the community should do so, because it deserves.
That's cool.
Indeed. So this communication is essential, so across the different disciplines of physics. So we have, and now also trying to understand I think the material aspect as well, with a question from Funky Lee, so who was asking, so for the neutron tunneling effect, so should we expect to see similar effect in the commercial supermirror neutron guide? The commercial one.
Yes. In the neutron guides, what happens is that in the neutron guides, we do operate with different thicknesses and different materials. Generally speaking, we we use, as I mentioned, the nickel and titanium, or nickel and vanadium, but nickel and titanium mainly. And what happens is that the configuration with the neutron guides, we are looking for super mirrors. We would like to, we are not interested in the tunneling. We would like, with the super mirrors, we would like to have in neutron guides, we would like to reflect as much as possible of neutrons over a large broad band. So in the super mirrors, at certain extent, there would be somehow tunneling, and that's why how can I say, we cannot see them easily, because they are a part of if there are tunnelings and so on, they are there, but they are a part of a large background of neutrons which were totally reflected. And that's why I was just asking Alan about Herb Mook and John Hayter, and of course Fermi about the super mirrors, because the super mirrors, they start with such a kind of resonators coupled, but they are coupled with the higher ones. So how can I say, it is not it might be seen, yes, but not detected easily.
Yeah, excellent. And then also on the superior, I just want also to put a little comment, because you were putting the reference to those super mirror with Fermi, Maaza, I think. So
Yes.
that was, which is exactly for the ESS, so one of the very original.
He's the innovator, yeah, he's the pioneer, yes.
Exactly. So all those different, neutron guide that we have here. So what would you see still in terms of challenge if we have a low flux? Or what would be, this is one of the things, how can we range the quality of those super mirror?
For the super mirrors, it's not really a problem. But for this type of for this type of structure that I was discussing, they need ultra cold neutrons and a high intense flux to have a high precision to be able to address this difference of 10 seconds. This is a really, sorry.
Indeed, for the so, but we're gonna have first so the more or less so the thermal neutron, and then later on so the cold and the ultra cold neutron.
Yes.
So that it should not be too much of a trouble then.
But definitely the how can I say, the ESS will definitely, such a high flux, and its equivalent in the US will bring a new dimension to neutron physics and fundamental science in general.
Yeah, very good. But we'll go in a stage approach. So this is why I think before we get that, we'll tune. We'll have possibility to tune and make sure that it's going to be fine. So Joe, you have a question. So please raise your question.
All right. Thanks, Christina. Malik, I hope you can hear me. That was a really great talk. I really appreciated it. Very interesting and very fitting for the year. I just had a couple of comments and one question. One of the comments is you mentioned Olga Nesson, and then I can introduce another international year. That was the periodic table, and he gave a wonderful talk at the opening ceremony on handmade elements, working at the Joint Institute of Nuclear Research. Anyway, so I kind of reminded me there's a couple of points that were interesting. One is this sort of anthropomorphic time scale, 14 minutes. That's about my lifetime. If I tried to swim underwater without breathing. So it just seems strange that something at an atomic scale would have a similar lifetime. But the other thing reminded me, because in an earlier life, I was measuring the density of helium, liquid helium. And it was we were trying to do ultra precise measurements, but then we realized that actually the accuracy of density of helium is a quite unknown quantity. I mean, it's actually, the uncertainty is actually larger than is, and people actually need that value. So when I looked at one of your opening graphs, I think Alan alluded to that. So between the beam, was it the beam method and the average bottle method? the uncertainties were one thing, but actually the average values were not overlapping with the uncertainty. So is the accuracy of the lifetime the thing that's most important? Because for some areas of study you want high precision, but I think you probably also want high accuracy. So is there an effort to try to disentangle? Why are they giving different results outside of the error bars? I would guess that's a basic question.
Thanks a lot, Joe. What I think is that both teams they are really adamant that their technique is giving the correct values. What is sure is that I think when there is such a discrepancy, there must be dialogue, and we have to find out: is it a technical one? Is it due to the fact that the neutron? There are some phenomena that the neutron is taking place in one or the other technique that we are not aware. You see that, how can I say, some colleagues are mentioning that there are some parallel universe. The neutron has a tendency to, how can I say, to behave in a way and come back to the normal. But anyway, these are speculations and so on. But it is necessary enter in dialogue. It's not to say that your mind is precise, is correct, yours is wrong. No, it is necessary to come in dialogue and find out the neutron is doing something in between here. It can't be that in addition, as you correctly, Joe have mentioned, it's not correct to say that it's only the error bar. There is a 10 seconds difference. The neutron is doing something funny here. What it is doing?
Yeah, interesting. Thanks. That's a good question.
Very good. So maybe, if you don't mind, Alan, we'll look at the webinar, because we had a question from Dr. Manikanda, who was asking about those cold neutron or ultra cold neutron. So if so, we should have those low energy. So in fact, so they have the lowest energy among all type of neutron. So how do you correlate? So the 1 dimension, 2 dimension, 3 dimension nanostructure, structural information. So could you please explain at the low dimensional interaction, so with this ultra cold neutron? Can you elaborate on that aspect?
Yes. At least in the, how can I say, in these conditions here, we have to more or less to mimic what is done in optics. And how can I say, the low and high band filters and so on, which are used in optics, we try to mimic that. And that is why how Schönborn came with these artificial crystals for neutrons, and that is how Fermi came with the idea of super mirrors and so on. So for the moment, I must say, for the moment, at least my knowledge myself is limited. I cannot really respond to the question of Professor Manikandan. What's the behavior of ultra cold neutrons on other type of dimension? That's, I am not able to respond to that question. What is sure is that if you allow me just to mention, Christine and colleagues, is that these activities of on high energy physics or fundamental science somehow is really taking place, taking momentum in Africa. If we take, how can I say, if we take, we are involving quite a number of postdocs and PhDs here in this field of neutron physics, trying to bring condensed matter to fundamental science. And the second one is that our colleagues in Morocco, for example, they are doing extremely very well. Recently, they have detected the most highly energetic neutrino, if I do remember. So these are fundamental science related to material science or technology related is really taking a momentum within the African continent. And really the case of, I hope that our colleagues from Morocco could come and speak about that experience of neutrino detection. Thank you.
Very good. So we'll have indeed Morocco speaking in July, so sometime this summer, so we can see also in connection also with representation, if she could answer that question. Thanks to her colleague.
It's a lot.
Very good. So we have, so Alan, please, so you have one more question.
Yes, pushing the optical analog again. I was absolutely stunned to hear that the uncertainty in gravitational wave interferometers is dominated by phonons in the mirror coatings. And that is apparently a fundamental issue that's being addressed now by changing materials and changing the temperature of the substrate and so on, in order to reduce the phonon dispersion literally in the reflections there. So, you know, when I saw the Kiesig fringes, it made me think of thermal diffuse scattering and how it's possible maybe to do an experiment varying the temperature or perhaps the materials in order to identify how much phonon component is in the unknown physics that you're dealing with for neutron lifetime.
Thank you so much, Alan. You are absolutely correct. In effect, our idea was indeed, because we have a tunneling, and the precision of the thicknesses is ±1 angstrom, and you are speaking about phonons. Yes, Alan, you have really touched the point. In effect, the fundamental science that we have to deal with is at that level. Unfortunately, I left the field of neutron physics because I have established myself in South Africa, and I have asked more or less to leave that field, but I kept it as a subject of interest. And definitely one idea to deal with is to, how can I say, we are dealing with the tunneling and therefore phonons and so on, and therefore it is necessary to carry out, to repeat the same experiments at different temperatures. You are absolutely right.
So maybe some interest.
Because Alan, if you remember, we measured we calculated the probability psi star, and we said that the minimum is in the middle of the absorbing material. Therefore, it's a must. The temperature plays indeed, because when you heat, you are disturbing the resonance conditions. You are right.
Yes. Interesting.
So indeed, maybe interesting study for the Lund University here.
Yes.
So that's really interesting to see what are the limits. So back to those questions, indeed. The performance, the limit, how can we get that? So we have one more question also from Faisal Barzi, so one of our former ASP, the African School Physics. So very interesting as well. So do you see a Brewster angle equivalent for polarized neutron?
No, there is no Brewster type whereby, how can I say, we see something equivalent, because the neutrons, they behave as photons polarized in the S state, not the P state, S state. So therefore, there is no way to observe the equivalent of Brewster. Indeed, Cliff Schull and Brookhouse tried to observe something equivalent, but they have not. No, as much as I'm aware, there is no equivalent of the Brewster.
Okay, so I think this is a good answer as well. Then do we have more questions for the audience, from the audience or from the panelists? Otherwise, I think that this is very, very comprehensible, informative, and at least it would be a great presentation as well for the school as well, for neutron scattering. So it's good that this is registered, and if I guess indeed in the audience we have a broad range as well of different persons, so who could also replay or maybe share as well, so with their colleague to get as well and build up more knowledge. So in Africa, as you said, so this is also something interesting as a kind of niche development. So that could be also from the theoretical point of view an asset. So yeah, so thank you very much for the time and for all the presentation. So we have, just a last question, sorry, that I see now. So from Fatma Zambri, who is saying, so how could you study the ultra-cold neutron, challenge or refine the prediction of the standard model of practical physics for the symmetry relation?
As I mentioned, how can I say, my background in, how can I say, high energy physics and so on, you can guess that it's at the 0 degree Kelvin. My knowledge is really small, is inexistent in that field. My interest in these colleagues is that when we saw the time life of the neutron, we thought about trapping it. That was the major, how can I say, major focus. Otherwise, really, the type of new physics coming out from it and so on, I cannot adventure in that. I cannot respond. I do apologize.
But I do like also the question. So I think Fatma, it will be interesting as well, potentially with CERN, with the ILL as well, because I know that they have been also working on those fields, some experiment and potentially from colleagues also from Lund University who are specialized in high energy physics domain. So we can bring the question to them and we will answer back. And please send your email, try to connect with us. So we will share as well, so the information of Professor Maaza by your email, if it's okay. So you have also some reference to the paper that you did. So thank you much. So maybe on this last difficult question, so we will thank the audience who have greatly appreciated from the number of messages that you have received. And connecting, I guess, from everywhere on the planet. So we'll see a bit more from the statistic, but thanks a lot for all of that. So a last upload, and then I will raise the presentation of next month, which will be next month much more simpler for most of our audience, which is looking at accelerating innovation. So looking at the interface as well with industry and research, creating value together. So this is going to be Dr. Rafaela Giametran, who is speaking from Trieste. And this is a spin-off from Electra, from a light source, Electra, which is in Trieste. So it will be also very interesting for you to connect back to the normal time difference now. So the time will be back to fixed in April. So around the different place and continent. So we will then have possibility to hear more, and you can see also from the Physics Matter page, so the coming seminar. So on this note, so thanks again for this presentation, and we'll see more than in 1 month and later on. So we'll stay tuned. Thanks a lot. Thanks, everyone.
Bye-bye.